So I'm going to talk about random oracles today. And first I want to give a very short recap about random oracles. And on the first day, John already went into random oracles, so what I'm writing is on this side, not on this one. John already gave a short introduction to random oracles, but I'm going to stress again the most important facts about random oracles. So what is a random oracle? It is an idealization of a hash function. So that's the basic idea. And why do we do that? So why do we idealize a hash function? We have the problem that there are a lot of protocols that use hash functions that kind of seem secure, but we can't prove them. So they're very hard to prove, or maybe there are even some impossibility results that show us that we cannot generically prove those protocols. So some hash-based protocols are hard or impossible to prove. Some examples of this include full domain hash that John already told you about. Another very important protocol is the Fiat-Shamir transform. You can use this to make signatures and non-interactive zero-knowledge proofs. And then there is the Fujisaki-Okamoto transform, which is heavily used in the construction of encryption schemes, and it uses random oracles. So you will find the Fujisaki-Okamoto all over in the, and Fiat-Shamir, I think, all over the NIST competition. And to prove this, we work in the random oracle model. So how does the random oracle work? We take the original protocol, we replace the hash function by a random function, so a completely random function from the set of all functions. Then we prove security for this protocol that uses a random function, and then conclude security for the original protocol. So we are somewhat cheating here because actually we cannot conclude it. It's a heuristic. But we have this heuristic that we say if we have proven it for a completely random function, then it's a very good assumption that it will also be secure for a sufficiently well-designed hash function. So what are the pros and cons of this approach? So the pro is we get easier proofs. I mean, right now I'm in the classical world. Just to say that, I will tell you when, as soon as we become quantum. It gets around impossibilities. So there are a lot of impossibility results that we can circumvent with this. And we tend to get very efficient protocols as compared to trying to make constructions without random oracle. I mean, it's always nicer if you can do it without random oracle, but sometimes the price to pay is too big. What is the disadvantage of the random oracle? Well, it is unsound in general. It is only a heuristic, and you can make contrived examples where the protocol is secure with a random oracle, but insecure with any possible hash functions, no matter how good it is. But the nice thing is that this does happen only when you make contrived examples. So the random oracle heuristic has worked pretty well as a way to proving the security of protocols and is widely used in practical theory. Yes? Can you speak a bit louder? No, it means that we can, for some protocols, we can show that we cannot find a proof for that protocol based on a hash function. But we can prove the security based on random oracles or things like that.
Shouldn't that be a problem?
Sorry?
Shouldn't that be a problem that you can take whatever hash function you instantiate the oracle with, it shouldn't actually work, but you're somehow claiming
Well, it depends probably on the exact result. So maybe the impossibilities are some impossibility to prove it from some generic assumptions or something like this. It's not a proof that it's insecure. Yeah. I mean, one would have to look at the particular examples, but I think if I remember right, I'm not fully sure. I think for all these three, there are some results that at least put big stumble stones into the way for proving the security without the random oracle. But I don't have the overview in my head of the literature, so I can't give you details on this. Okay. Yeah. So, unfortunately, I cannot because the aspect ratio of this is given by the physical size of my tablet. So, I mean, I could reduce it, but it wouldn't make this bigger, unfortunately. I will also actually use this if I want to copy a snippet from one page to keep. So I plan to use this real estate in nicer ways later. Okay, yeah, and an example of the random oracle was already given in John's talk with the proof of full domain hash. I will not go into that again because we are focusing on the quantum setting, but let me first recap like in a generic abstract way how the random oracle model works. So what do we do? So when you want to work in the random oracle model, there's basically a 4-step recipe of what you need to do in your proof. So you take the existing security definition, for example, unforgeability of signatures. This definition is usually written as some game where a few things are randomly done and adversaries are called and so on. And then you add as the first step just a step where you say we pick some function h from the set of all functions from x to y, where x and y will be throughout the talk the name of the input domain and the output domain of the hash function. So imagine n-bit strings and m-bit strings, for example. I just write x and y because it's shorter. So we add this in the definition game. So now we have some completely random function. This notation here means pick randomly. And then we give h to everyone as an oracle. So all algorithms in the game will have the possibility to evaluate the function h as just one step. They don't need to compute, they just have a magic operation in their source code, evaluate h. And then, in addition, you replace honest hash calls by h. So anywhere where your original, say, signature scheme says apply the hash function, you now apply h. So what the honest participants do is pretty well defined because we just put explicit H's, but the adversary may do whatever it wants with H, so we are not restricting the adversary in that respect. So let's keep this in mind as what the random oracle does. Maybe I will do some keeping in mind here. Okay, so now the second question we may ask, besides how does the random oracle work, is why is the random oracle so useful? So I said it makes proofs easier, but what about the random oracle in the classical setting is it that makes all the proofs so much easier? And the answer is, I mean, there are a bunch of things, but probably the most important technique that makes the proofs easier is what we call, or what at least some people, including me, call lazy sampling. So what does lazy sampling mean? It means that you replace your hash function h by a hash function that is so you have your hash function in our model is a completely random function, and there's a way to emulate a random function by just evaluating its outputs when we need them. So all outputs are randomly chosen, and instead of choosing everything at the beginning, we can choose the outputs when we need them. So the idea is we replace a uniformly random h by a lazy h. So initially this is an empty function, which has for any input an undefined output, and then for any input x on the first hx query, so whenever we use an x input to the hash function that we have not asked before, we pick the result randomly on demand. And upon further queries, so we don't always answer randomly when we are queried, so upon further queries, we use the cached result. And all this does is actually, instead of choosing all the answers in the beginning, it chooses them when you need them, and it's reasonably simple, at least on an intuitive level, to see that there is no difference when you choose it, as long as you choose it. And the great advantage of this is that the random function, random oracle, so if we define a random oracle as a random function, is completely indistinguishable by any adversary, by any number of queries you do, from a lazy sampled random oracle, which means we can just use the lazy sampled random oracle in the proof instead of the true random oracle. And why is it useful to use the lazy sampled oracle? Because we can now we can reason about independence of values more easily. For example, if a certain value has not yet been queried, we know that it will be independent of all the values that we have already chosen, because it hasn't been chosen yet. When we query it, it will be as a completely random value. And this reordering of the random choices is very helpful for cryptographic proofs. And another very useful thing is we can what we call program the random oracle, meaning we can, for example, when something hasn't been queried yet, we can just say, instead of picking it randomly, we put something there that we want there. I mean, we, the person who does the security proof. And at least as long as this value looks like a random value, no one will notice. So by keeping track of the queries that are being made, we can know which values we can still change and so on. And these two things are probably the most important things for security proofs in the random oracle model. Yeah. And they also show the difference between the random oracle and real hash functions, because these things that I'm mentioning here, like independence of different values or programming the hash function, it does not make much sense. It's not a meaningful thing to say a certain output of the hash function is not yet defined, because the code of the hash function is completely known and these things. So this is why we like the random oracle. Okay, so this concludes the kind of a recap of the classical random oracle with stress on the things that are important from my view for the rest of the talk. Are there any questions about the classical random oracle at this point? Okay, so then let me come to the quantum random oracle. So far I've only talked about classical cryptography. So I have shown you that I have explained why the random oracle is useful. I have explained to you how it is defined. But I've done it with completely ignoring the quantum situation. So if we want to do a quantum random oracle, we run into two problems. So problem one is probably the easier one. So if we ask ourselves, so imagine you would say we just keep the definition of the random oracle as it is when we go to the quantum setting. So what would happen? The classical random oracle can only be evaluated classically. I mean, by definition, it's something you send one value to it and it gives you one value back. No superposition. However, a real-life hash function, no matter how well designed it is, can always be evaluated in superposition. By evaluating in superposition, I mean that you can do queries that are of this form, like let's say, just as an example, you have a superposition of all possible values x, and you use the oracle, the hash function to map this to a superposition of x and hash of x. So you can always do that, as long as you have the circuit of the hash function. So this is something you can do in real life. And now it would be a very bad model if you would say our idealized hash function does not allow the adversary to do superposition queries. I mean, it is not at the first glance obvious whether this matters in the end or not, but it definitely seems unfair. And actually, it turns out that it also matters. So one thing that's easy to see is that if you can do these things, you can run Grover's algorithm that that was described, I think, on the second day, to break, for example, to invert the hash function in time square root of number of outputs, while if you have a classical function, a classical access to a function like this, then it will take number of outputs queries. So at least there is a big difference in time. That still doesn't mean that maybe if you only care whether something takes polynomial time or super polynomial, then this doesn't matter so much, although practically it matters a lot. But there have also been relatively recent results which show that there are at least some contrived protocols that are, contrived but quite simple, that are secure with respect to classical random oracles, but are insecure when you actually model random oracles in terms of when you allow superposition queries. I'm not going into that, but I prepared a little handout with related work. You find it on the, when you go to the schedule, Thomas has put a link there somewhere. I mean, I'm told. So what do we do about this problem? Fortunately, the solution is quite easy. What we do is allow superposition queries in the quantum random oracle model. So if you look on this side here to the definition we had, we need to change this in two places. So we still pick the function randomly, but we don't give h to everyone as a classical oracle, but instead we give it as a quantum oracle. So to just summarize only the changed things, we say or only the important things, we still pick h as a random function, but we say give this to everyone as an oracle, where this notation here is sometimes used to mean an oracle given with superposition access. So I will, in this talk for a while, use this notation, and then at some point I will start dropping it because it's just very tedious to write it all the time, but I will let you know when I start dropping it. So what does it mean I give h as an oracle? Well, it is also something we saw on the second day in the quantum overview. It means that the adversary, instead of getting some classical box that applies a classical evaluation of h, the adversary gets a box that computes the unitary UH that maps values x and y to x and y XOR h of x. I mean, there's some freedom in your modeling whether you use XOR or some other group operation and so on. But for this talk, let's assume that it's always the domain is a set of bit strings, and therefore you can use XOR. And, well, now the adversary has access to this thing, and therefore can do all these kind of evaluations that it can do with the real-life hash function, and the model is, again, much more realistic. It is still, I mean, the unsoundness that I mentioned earlier is still there, but at least it's not this glaring kind of one anymore where we have definitely overlooked a very important thing. Oh, the cat needs to be closed. Okay, so to illustrate this, let me first write down two examples, not examples of proofs, this will come later, but just two examples of how security statements in the quantum random oracle would look like. Basically, mostly I'm going to show you that they look very unexciting, so nothing complicated happens. So example one would be pre-image finding So normally if you would, so like we look at the following classical, not classical, at the following non-random oracle property, which would be something like for any t time adversary A, we have that the probability of winning is smaller equal epsilon. In the following game, we pick a random value from y, we run the adversary with input y, and we set the flag win to true if f of x equals y. Yeah, so given a random value, we want to say that it's hard to find an input to f that outputs the random value. By the way, to the audience, does someone know how this property is called? I mean, it's almost one-wayness, but one-wayness is defined where the y is chosen a bit differently. I don't know whether this property has an established name. So if it has an established name, please let me know. It's a natural property, but I don't know the name. Well, in any case, this property we want not to translate into the random oracle model, and that turns out to be relatively easy. So all we do is we write it in the quantum random oracle model. It still says for all t time A, the probability of winning is small, but the game has slightly changed. So now we have this picking of the function. We also pick the y as before, because up here it was picked randomly. Then we run the adversary on y, but now the adversary has to get h, oracle access, so we give it as a quantum oracle, and we say we win if, and now for simplicity I say the function we are looking at, whether it's pre-image finding is hard, is not something built from the random oracle, it's just the random oracle itself, just to have a simpler example. So we might say we win if h of x is y. So this would be now a statement in the random oracle model. You may want to refine it somewhat because, I mean, of course, the time that the adversary runs will be an upper bound on the number of queries that the adversary runs, because you take at least one step, but you may get more fine-grained statements about the security level if you say also, like, it's for any adversary that makes at most q queries to the adversary and runs at most t time, you want that the probability is smaller than epsilon for some parameters qt and epsilon. And in this language, we can, this thing actually holds. So while it's not as simple as proving the pre-image finding hardness with the classical random oracle, it can be done. And we have the following fact that I'm not going to prove here, that indeed the probability of winning is at most q square over 2 to the minus m, where m is the bit length of the outputs. This is basically the analysis of the fact that the Grover algorithm is optimal, and there are there are a bunch of different results that give roughly this bound. I linked to one of them in the handout if you want to read it up. So any questions about this kind of definitions? Yeah.
I got lost. You said it was different from.
Sorry?
So your definition of pre-image finding, you said, is different from one-way function.
Yes. In one-way function, it is. So in one-way function, we don't pick y randomly from the domain in the definition, but we pick x, and then y is f of x, and then the same thing, which for a permutation is equivalent to this. So one-way permutation is actually often defined like this because it's equivalent, but for a function, even for a random function, it is not exactly the same distribution. It is similar enough not to matter in this example, but I can't call it one way because then I would be angry with myself. But it's almost one way. It's almost the same as one-wayness. Example 2. Collision resistance is also something that we could state. If we can spell it, yeah, I think I managed. So there I will not go through first classical, then quantum, and so on. Let me just state it. So we pick H randomly. Then we run an adversary that is supposed to give us 2 inputs. And the adversary doesn't get any outputs, but it gets, it doesn't get any inputs. It only gets access to the quantum oracle, and it's supposed to give us 2 values, x and x prime. And it wins if f of x, no, I'm in the wrong line, oops. It wins if these 2 values are not the same, but their hashes are the same. So this is another fact we could state about the random oracle, and this one is actually considerably harder to prove than the one-wayness, but I think it might already been, well, it's already quite a while, maybe almost 10 years ago. It was proven. I just state the fact, and you find the references in the handout. So here we have that the probability of finding a collision in a hash function is q to the 3 over the size of the output domain. Like classically, we would have q squared, so we do get differences. And by the way, this is also tight because there are algorithms that can do it this fast. So this was a mini introduction into what the QROM is about, also giving you 2 important facts already to, I mean, these are examples, but they're also very important facts that you may use over and over in security proofs, because if you can just reduce something to an existing result, why reprove it? So especially, especially this one, things are a bit delayed, especially this fact I find is used quite often as part of a security proof. Okay, so let me now state the pros and the cons of the QROM that we can compare with the classical case. So, some pros are it allows to overcome impossibility results, like the classical one. There are some things we can't prove without, and we can prove now. It allows it gives us more efficient protocols. So for example, all the 3 protocols that I mentioned earlier, full domain hash, Fiat Shamir, and Fujisako Komoto, have been shown secure in the QROM, although depending on the protocol with sometimes much worse, sometimes somewhat worse parameters, and also in some cases with additional side conditions, but at least we get some results for them. And one con is that the unsoundness still is there, but at least there doesn't seem to be any evidence that the unsoundness, the generic unsoundness, gets any worse. However, you'd notice maybe that one of the things that I mentioned in the pro column for the classical ROM, namely gives us easy proofs, is gone, because unfortunately the proofs are harder than in the classical case. In some cases, much, much harder. So the easy life is over, unfortunately, now. So why is it that the proofs are now harder in the QROM? What makes the QROM so much more annoying than the classical oracle? And remember lazy sampling that I talked about in the classical case. And in lazy sampling, we pick every output of the random oracle when it is first sampled, when it's first requested. And therefore, we have really nice control about the fact that things that have not been queried yet are truly random, and there's no way to know them because they haven't even been decided yet. And that makes everything nice. But now lazy sampling does not work anymore. So that's unfortunate. And why is that the case? Look at the following examples. Let's say the adversary with oracle access to H does the following query. It queries, some words are harder to write than others. It queries input 2 to the minus n half sum over x, so just the proposition of everything. This gives back the state 2 to the minus n half of cat x in one register and cat hash of x on the other, so we should put a 0 here in addition. And this looks harmless at first glance, but actually what it means is that all values of h are now involved in the state that goes back to the adversary. So we can't say pick just one h, we have to pick them all outputs of h. And this breaks the lazy sampling because now even after one query, the adversary has forced us to pick the whole random oracle, and nothing is random anymore. So at least from a simplistic point of view, we would say, okay, the adversary has learned everything about the random oracle. Of course, it's not very accessible, this information, but it is there. And now we will need much more complicated arguments to say, well, it is there, but the adversary cannot use it. Yeah, and this also applies to reprogramming. If we change some output, I mean, maybe if I change h of x at some x, the adversary will not know, but it's harder to show, and also harder, like if I want to decide which one, I need to kind of know what the adversary has queried, but the adversary, I mean, I can't measure the query because this disturbs what the adversary does and so on. So lots of challenges. And for a long time, it was believed that lazy sampling is just completely out of the window. But later I will talk about the compressed random oracle, which brings lazy sampling back to a certain degree, and unfortunately in a way that is much more complicated than in the classical setting. But for now, we will not go for that yet, but what I will do in the rest of this of the lecture is I will show you several proof techniques that one can use with a random oracle that do still work. Okay. But first, are there any questions about the things so far? Okay, so I will show you 3 techniques in increasing level of difficulty. So, technique 1 does not really have an established name, I think, so I will just call it replacing the oracle. So, the underlying idea behind this technique is that if I have a random oracle, that is a random function, and I replace this random function by a different function that has the same distribution, so also uniformly random, then no one will tell the difference. So at the first glance, this sounds stupid. So I replace same distribution. What's the difference if it's the same distribution? But I will explain this in a second. So replace h by a different function chosen with the same, or in somewhat more advanced settings, with a close distribution. So let me also show you first, before I go into a real example, explain why this can make a difference. So, for example, for a permutation pi, we could replace h by pi after h. So we apply pi to every output of the random oracle, and pi, like if you apply the same permutation to all outputs, you still get a uniformly random function. Why does it then make any sense? Well, the reason why this having pi after h in your security game can be nicer, depending on the details of what you're doing, is that now, though it has the same distribution, now it is, if you then use just h, you can actually, if you have an output of this thing, you can very easily apply pi to the -1 to it, because that's just h. So suddenly you're in a situation where in your reduction, you can do proof steps where you apply the inverse of a one-way permutation or things like that. So that's basically the idea why you may want to do replacements like this. In the proof of full domain hash, for example, you would do things like that. But I will not do the full domain hash proof, because it actually needs some extra techniques in addition that go beyond this. But what I will do is a slightly contrived but very simple security property, and show how the technique works on that example. So the game we are looking at is that we pick the random oracle uniformly, as usual. Then we let the adversary run with oracle access to h. And from now on, I will, because I have to write this thing a lot, I will just put h and not h in cats. Notation in different papers differs. So some papers put this cat, some papers don't. Some make maybe some symbol to denote if it's classical, and by default is quantum. So you just have to check carefully what the paper means when they're doing it. Unfortunately, some papers don't tell you, then you don't know whether they are in the quantum random oracle model. That's a bit annoying. Okay, but what do we want to do? So you may recognize this is quite similar to the collision resistance, but we have a different winning condition. We want that the adversary wants to find inputs x and x prime so that the hashes of x and x prime XORed together equals x XOR x prime. So the inputs should have the same XOR as the outputs. This is easy if x equals x prime, then we have 0 on both sides. So additionally, it should be that they are not equal. So that is the thing we want to analyze in this example. So what we want to show is the probability to win is sufficiently small. We will see later how small or big. Okay. Is the setting clear or are there any questions about it? Okay, let's, and here I will now make heavy use of having this unused real estate. So I will copy the games over here so that they are left for reference.
Your technique here, you're talking about doing this at the very beginning of the experiment, right?
Yes, exactly, like throughout.
Okay.
Not.
So isn't it like immediate because the distribution of the oracle is the same? So I mean, there's nothing special about quantum here.
Yeah, exactly. It's just this technique works classically in the same way, and you may also use it in classical proofs. It just becomes more. It is also the most basic technique. I mean, I don't need to prove any theorem for this technique. It's just one should be aware of it because it's the one. It's basically, I think it's the only thing from the classical realm that still works nicely. And it's like the first random oracle, quantum random oracle proofs were heavily using this technique. Okay, and now we will try to use this technique. So the idea is that now I will replace the function h by another function that is distributed the same way. I have many choices what I can do, but I choose one that will make the proof go through in the end. So I still pick h for the moment for reference, but I define a function g that is the function that maps x to a hash of x XOR x. Okay, so I mean this notation here, I'm using the notation like if I want to describe a function in one go, I just say it's the function that maps x to this. If you are familiar with functional programming, you would rather use this notation, but I'm not sure whether this community is familiar with it, so I'm using this notation to compactly write down a function. And it is relatively easy to check that for a random function h, this function is also random. Of course, if h is known, then this will not look random because it's completely determined by h. But if you pick h, then construct g, and then forget h, then we will definitely have g having the same distribution as the original h has. And now we give g to everyone. So the adversary gets G, makes two queries. Then the adversary wins if G of x is, no, not, if G of x XOR G of x prime equals x XOR x prime, and they are different. And this will have exactly the same winning probability. So winning probability in G2 equals the winning probability in G1. Let me highlight the things where I changed things. So I introduced this thing up and changed things here and here. Ooh, what an ugly yellow. It's a really bright yellow on my screen, but it's kind of a bit moldy over there. Okay, so why was this useful? Well, now we can actually simplify things, and so game 3. Now I'm just doing some classical simplifying. Just plug in the definition of G again to compute H. Well, to express things in terms of H. So I can write, I have this step still. I skip the definition of G because it will not be used explicitly. Then I need to use a slightly modified adversary A tilde that gets H, but that internally using, whenever A would have made a G query, A tilde computes the answer of the G query using an H query. You need to be a bit careful about whether you can actually do this as a quantum circuit, because you can't write down H and then compute the full function G. You need to manage to simulate G queries using an oracle for H. But at least for this specific function, this is relatively simple to do with a small quantum circuit that does only one query. In more complicated cases, you may need several queries, but most of the time it works. But make sure to check that it really works, because you can also write down functions that you could write definitions of G that you cannot evaluate using an H oracle. Okay, but now the interesting thing is what happens to the winning condition, because now this becomes H of x XOR G of x prime XOR x prime equals x XOR x prime, and they are different. But this condition here is actually just the same. Like, these x's cancel out, these x's cancels out. Oh, yeah, there should be an h. So it becomes h of x XOR h of x prime is 0, which is just the same as h of x equals h of x prime, which is the condition of collision resistance. So we have now two important facts here. The probability of winning still hasn't changed. And this thing, because this is just the collision resistance property, where I mentioned earlier that this is a known result. So this is smaller equal O to the Q3 over, oh, not over 2 to the M, just like this. So we have now proven the security of this slightly contrived of this slightly contrived goal. But you may often have reductions like this if you want to prove some fact that appears in your proof. Some condition cannot hold. You might be able to just do it with proofs like that and reduce it, for example, to the collision resistance, or even more often to the pre-image finding, for example. Or it is something that you use to bring the game into a certain form that the challenger can know, I don't know, pre-images under some function of some outputs, as I mentioned, with the pi after h. So there are a lot of ways how this technique can be used. I just wanted to make sure that you are aware of it. some facts about it. This also works for some special cases of full domain hash. Not for the generic one, but in certain cases when you have additional properties of the trapdoor permutation or trapdoor injection that you use, you can actually use this technique. Again, references are in the handout. And sometimes nice to replace by indistinguishable H, so not, or let's call it G in this case. So instead of having something that has the same distribution, you have just something that is indistinguishable from a random oracle. And for this, there's a useful technique that shows that if the individual outputs are indistinguishable from random, then the function as an oracle is also indistinguishable, which is a non-trivial result. So I'm not going to go into the details, but I also linked this in the handout in case you happen to need this. Okay. Any questions about this? Okay, so this was the most basic technique that we can use in the random oracle. Now I will come to the second technique, which is called the one-way to hiding lemma. Also known as O to H. So this is this has turned out to be quite useful for proofs, like especially proofs of encryption schemes and so on have very often use it, and there are also already a bunch of different variants of it. I will only explain to you the original O to H lemma, which is the simplest one, which has is not very general and so on. It was actually just a lemma that I proved in an appendix because I needed it for a specific proof, but I was lucky to formulate it in a general way, so it turned out to be reusable. So maybe this is a lesson if you have some auxiliary result, if it's possible without too much work to formulate it in a way that is not specific to your problem, then maybe do it, because if you are lucky, that paper can actually become more famous for the auxiliary lemma in the appendix than for the actual result in the paper. So what is one-way to hiding about, or what kind of problems does it want to solve? So when you use the replacing the random oracle technique, this replaces the random oracle from the very beginning. So before anything else happens, you change your random oracle to some other random oracle, and then everything runs in the same way. So change is in the very beginning, and we have 100% consistency. So if we query the random oracle, and at one point we query it later, it will give us the same output. There is no such thing as maybe in the beginning it gives us one answer and in the end it gives us another, which is something where we would then be in danger of the adversary noticing that. But instead, the replacement is completely consistent. But sometimes we do not want that. So what do I mean by an inconsistent replacement? This would be something like change the random oracle somewhere, it's like maybe even in the middle of the game or something like this, but still use the original output value h of x somewhere else. So now, instead of having two places in the game where we would get the same answer, we now have different answers. And this is something the adversary can in principle tell apart. So what we need to do is then we need to hope that the adversary doesn't notice. Yeah. So classically, we can do these things relatively easily because we can just say, as long as the adversary did not query this value on the new value, or, well, as you can keep track of the query, so you can tell whether the adversary gets both values or not. And if the adversary doesn't get both values, which you need to prove, of course, but if you can prove that a certain query hasn't been made, then you know everything is fine. So in the classical setting, these inconsistent replacements can often be handled quite easily. And but let me flesh this out a little bit more, what you do classically, in order to be able to then explain what we do quantumly. So classically, we have that the adversary cannot notice unless the adversary queries the changed value. So in somewhat pseudocode math, this would mean that the probability of winning in the original game minus the probability of winning in the new game, where we have replaced things, and of this the absolute value, would then be smaller equal the probability that the adversary queries h of x, where x is the input at which we change the random oracle. So you can show something like this. And actually, this is kind of incomplete. I didn't say query h of x in which game. The nice thing is that we have the choice which one to use. This is true in both cases. So let's say in the new game. So often the new game is the easier one. So analyzing this thing in the new game is easier. And now you have here something simpler to analyze. It's not an indistinguishability of two outputs. It's just about whether a certain value x can be guessed by the adversary or not. And it's also in this new game where we have maybe already removed some dependencies and replaced some value by actually just a random value and so on. And here we can already also see why we call this a one-way to hiding theorem. Because here we have an indistinguishability, and indistinguishabilities are often like, I cannot tell this value from that value, at least maybe not this particular expression, because it's like just two technical games in the middle, but the part of the big thing is usually something like I cannot tell one value from another, so its difference of probabilities has to be negligible, while this is a one-wayness kind of property, so I cannot guess x. So it's somehow one-wayly used in the game. So the one-way to hiding is often used to have a hiding-like thing deduced from a one-way-like other property. And this is why, how the name came up. I mean, in the original use, it was exactly like there was one hiding property, there was one one-wayness property, and it was used. But if you take the words hiding and one-way in a little bit more general sense, more like indistinguishability and guessing, then it still explains how the one-way to hiding technique is used. So the question is now, can we do the same thing in the quantum setting? Does it make sense to talk about, to do this? And now we have 2 problems. 2? I don't know. We have problems. Can we do this quantumly? And the first problem is that we can't even write down this formula. I mean, it's not even a question about whether this formula is true or false. It is just not a meaningful formula. Why is that? Help. I got lost. Okay, yeah. I think I got reoriented. So the main problem is that this thing, like, what would even be the meaning of this thing in the quantum setting? Because we do not have, like, we could query everything in the first query, for example, by doing a superposition query. And we are also not allowed to measure what we have queried because this disturbs things and so on. So that's the problem, that we cannot just even hope for this thing to appear. But it will turn out that there is a replacement for this that works in the quantum setting. So let me copy this formula for future reference. And what I want to do is, I will not show you the one-way to hiding theorem right away, but I will give you an example protocol, in this case even one of practical relevance. I mean, it's a very simple encryption scheme, but not irrelevant in principle, and I will show you how to prove the security. So what will I be analyzing? So I define an encryption scheme, and to encrypt a message M, what I do is I pick some random R and I compute f of R, where f is a one-way permutation. Now, actually an encryption scheme should have a public key and f should depend on the public key, but just, and then you can decrypt with the secret key. But since in this example decryption does not actually occur, I'm slightly simplifying and I'm just saying f does not depend on the public key, it's just a one-way function, a one-way permutation, just to have less things notationally in my game. So it's not really an encryption scheme because you can't decrypt it because there's no trapdoor, but that does not at all change the analysis. So it's just a notational simplification. So what the encryption scheme does is it applies a one-way permutation to some randomness R, and then it takes the message and XORs it with the hash of R. I'm not sure, but this might have occurred in your talk already, yeah. But of course now we are in the quantum setting, and things can be more complicated. And my claim is that this is int CPA secure. So what does int CPA secure mean concretely? Let's write it out in the random oracle model. So the game that we want to analyze, it first picks the random oracle as a random function as usual. It picks a bit B that is 0 or 1, because in the in CPA security game, we will encrypt 1 out of 2 messages and the adversary has to guess. Then we run the adversary. It gives us 2 messages, M0 and M1, and it has superposition access to the random oracle. Normally it would get the public key here, but since I simplified that away, it doesn't get anything. Then we encrypt with the encryption scheme above the message MB. We give this ciphertext to the adversary, who can do more oracle queries, and it has to output a bit B, that is a guess which of the 2 messages was encrypted, and the adversary wins if B prime equals B. Yeah. So this is the in-CPA game in our situation. And what we want to prove is the, okay. What we want to show is the probability of win is very close to 1/2. Any questions? Good. Yeah, and the first step in such a security proof is usually to unfold all our definitions. So we have the definition of the encryption scheme, which I unfortunately didn't copy over. Wait, let me do that. Okay, this is the encryption scheme. So we can just plug it in. So this is not yet any random oracle technique. This is just a preparation, but we need to get to the point where we can actually do things nicely. So we do not change anything about picking the random oracle. We also don't change this line. But now, since the function enc is just invoked once, we can pick the randomness that it will use for encrypting in the very beginning. Then we call the adversary. Now, instead of encrypting here MB into C and then giving this to C, I will just give those 2 terms directly to the adversary. So the adversary gets f of r, where r is the thing from above, and m XOR hash of, mb XOR hash of r. Nothing much changed. We have that the probability of win in game 2 is the same as the probability of win in game 1. Okay, any questions about this? Okay, and now comes the interesting step. So the intuition why this thing here is secure is that we have MB here, which contains information about B, but is XORed with an output of the random oracle. And our intuition is that H of R is basically random. Because R is not known to the adversary only knows F of R, which makes it from which it's hard to get R, and therefore H of R is probably not queried in whatever that would mean in the quantum setting, so we can replace it by a random value. So let me just write this down first, and then we will talk about how this could be analyzed. So not much changes. I will use the magic of copy and paste. So what changes is that now we do not have the random oracle of R here, but instead we just put a value Y here, and Y is also just uniformly random. So this is the only difference, but it's a very drastic difference, of course. So we get this game. What we need to see is, of course, that game 3 is indistinguishable from game 2, so that the winning probability does not change much. Oh, I forgot the winning. Oh, I forgot it also up there. I mean, it should be everywhere. So we need to show that the winning probability doesn't change much. I will come to this afterwards, but first let me wrap up the rest of the proof. Because if you look at game 3, we have MB being sought with a random value, which is not used anywhere else. So this is a one-time pad and hides completely MB. And B is not used anywhere else, so we get that the probability of winning in game 3 is exactly 1/2. So if we can show that game 2 and game 3, the winning probabilities are very close, then we know that the winning probability in game 1 is also very close to 1/2, which is what we wanted to show for security. Now, classically, using the statement that I had the thing here, it would actually be quite simple to show that, to show this indistinguishability between the games. So classically, what we would do is we would have the fact that the probability of winning in G2 minus the probability of winning in G3 is bounded by the probability that AH queries R in G3. And now, how likely is it that AH queries R in G3? Well, if you look at G3, this game here, R is picked here. It's put through the one-way permutation given to H, and is not used anywhere else. So it's a quite elementary reduction to the fact that F is a one-way permutation to show that AH cannot guess R, and therefore also not send it to the random oracle. We have eliminated all other dependencies on of R, so this thing would then classically be shown to be approximately 0. The exact value depends on F, of course, but it's something very small. So the question is, how can we do this thing quantumly? And I think this is as good a point to interrupt before we have our coffee break, because I think it would start in 3 minutes. So I leave this as a cliffhanger till the next session. Thank you for your attention.